Okay, today we're going to start talking about logarithmic functions. So we want to start by seeing if we can find the inverse of the function f of x equals b to the x, our exponential function. So remember when we talked about finding inverse functions, we talked about changing our f of x back to y, and then interchanging the x and the y. So we now have x being equal to b raised to the y power. Okay? But we don't really have any way to solve for y now. We don't have any way to undo that exponential. And the way that we're going to attack that is by what are called logarithmic functions. So when we talk about a logarithmic function, here's what we're talking about. When x is greater than 0 and b is greater than 0 but not equal to 1, y equals the log base b of x means that b to the y is equal to x. So if we look at where these things are, this b to the y, well, here's b down here is the base, and it's now been raised to this y power. And that's equal to this value here at x. Okay? So the logarithmic function is actually the inverse of the exponential function. Okay? So f of x equals to log base b of x is the logarithmic function with a base b. Now sometimes if we don't see anything down here where the b is at, that's just going to always be the standard form for a log base 10, which is the normal base. If we change the base of our log to not be talking about powers of 10, then we have to indicate what the value is. So we want to take each of these equations that are in logarithmic form and write them as exponentials. So if we follow that same kind of pattern that we looked at before, the base of the log becomes the base of the exponential, and it's going to be raised to the power of the number on the other side. So this would be 5 squared is equal to x. That would be the exponential form of this logarithmic equation. Right? Same thing in part B. The base of the log raised to the power that's on the other side. So b to the third power equals whatever this value is that's left, 64. Okay? So this is how we take a log function and write it in terms of an exponential. We take the base of the log, and the base of the log becomes the base of our exponential, okay, the base of our power. And we can go in the reverse as well, okay? Since I know that the base of the log and the base of the exponential have to be the same, I know that this is going to be a log base 12, okay? And since 12 squared is equal to x, I know it's log base 12 of x has to be equal to 2. And I can check that by going in reverse. 12 raised to the second power would leave with just the x left over. Okay, so I know I've got everything in the right order. So if we look at part B, okay, e is the base of my exponential, so e has to be the base of my logarithm. I know that the exponential was the piece that was over by itself to begin with, so it's going to be the log base e of 9 is equal to y. And we're going to see more about this log base e and what that really means and how we can write it in a special format. Okay? But first, here are some basic properties of logarithms. Okay? If I have the log base b of b, when these two things right here are identical, when they are the same thing, that logarithm is always going to be equal to 1, because b to the first power would leave me with b. The log of 1, no matter what the base is, the log of 1 is always going to be 0, okay? Because anything to the 0 power is 1. Okay? Log base b of b to the x. I've got the base of the log is b, the base of this exponential is b, which leaves me with a solution of whatever this exponent is up here. So notice that those two things are the same. Okay? So for example, if I had log base 3 of 3 to the 4th, that would just be equal to 4. Since the base of this exponential and the base of this log match, then the 4 becomes my solution. Okay? And likewise, if I take b raised to the log base b, again, the base of the log, the base of my exponential match, which means my solution is whatever I was taking the log of. So the b raised to the log base b of x is just going to be equal to x. And these are some basic properties. Okay. So if we evaluate these expressions, log base 4 of 4 to the 5th power, well, the base of the log and the base of the exponential are the same, so this would simplify to just the exponent, which is just the 5. Okay. Number 2, 6 raised to the log base 6 of 9. Again, the base of the exponential matches the base of the log, so 9 is the solution there. Okay. So when those two things match, whatever I'm taking the log of is my solution. When the exponential and the log have the same base, the exponent is my solution. Okay, so moving on. If f of x is equal to the log base b of x, our basic log function, or kind of our parent function if we relate it back to the things we've done before. Okay, the domain of the log function is going to be 0 to infinity. Okay, I'm only allowed to take the log of positive values. Okay, so this value here has to be between 0 and infinity. The range, however, could be any real number. Could be negative values, could be positive values. If you remember, we talked about the y-intercept for the exponential function was always at 0, 1. Since exponentials and logs are inverses, we have an x-intercept for the log function, which is at 1, 0. When the base of my log is greater than 1, the function is always increasing. The values are going to continue to get larger. But when the base of the log is between 0 and 1, then the function is going to continue to decrease. And instead of a horizontal at y equals 0, as we had with the exponential, we have a vertical asymptote at x equals 0. Okay? So let's take a look at an example. If we look at the function of log base 2 of x, we know that we're going to have an x-intercept at 1, 0 because we're not doing any transformations. We're not adding or subtracting anything to x or anything to the log function itself. So if we think about evaluating f of 4, so we'd have log base 2 of 4, okay? And that's really equal to our y value. So what we're really saying is 2 to some power gives me 4. Well, that would be 2. So I know that I have another point on my graph at the coordinate 4, 2. If I think about the value of 8, then I'm taking log base 2 of 8 gives me some y value, which means 2 to the y is equal to 8. And 2 to what power gives me 8? Well, that'd be 2 to the 3rd power. So I'm going to have another point out here at the coordinate 8, 3. Okay? Now notice the base of our log, our base of 2 is greater than 1, so we know the function's increasing. We know that we still have this horizontal asymptote here at x equals 0. So what's happening is this function is coming up along the asymptote, and it's going to curl out, and it's going to continue to increase as x's get larger. Okay? And now all these logarithmic functions have the same basic shape. They're all going to come up along that asymptote, go through 1, 0, and then continue to increase, and the rate of the increase depends on the size of the base. Okay? The larger the base, the larger the increase, or the faster the rate of increase. Okay? So let's look at another one. Here's the function log base 2 of x plus 2. Okay, so here's an example of our transformation. Okay, when I add 2, when I do something directly to x, remember that means we're going to be moving it either to the left or to the right. Since we're a plus 2, that means we're going to go to the left 2 units. So my asymptote, which used to be at x equals 0, is now going to fall over here at x equals negative 2. Our y-intercept that used to be at 1, 0, or our x-intercept that was at 1, 0 is going to shift 2 units to the left. So it's going to be at negative 1, 0. we had a point that was at 4, 2, so it's going to shift 2 units, and it's going to move over to 2, 2. Our point that was at 8, 3 is now going to shift 2 units to the left, and it's going to move over to 6, 3. But we're going to keep that same basic shape of that logarithmic graph. So those ideas of transformations are still going to hold up just like they did with every other graph. If we do something directly to the x, if we add or subtract something to x, we're going to shift the graph left and right, which is going to also move the asymptote. Okay? If I were to look at my domain now is no longer 0 to infinity, but my domain is going to be negative 2 to infinity. And my range doesn't change. It's still going to be negative infinity to infinity. And I still have my vertical asymptote, but now it is located at x equals negative 2. So we have those transformations applying to logarithmic functions, applying to exponential functions, just like they did with quadratics and cubics and square roots. We still maintain those same ideas of having those transformations of the graphs. Now, here getting back to what we referred to earlier, we talked about that log base e. That log base e is what we call the natural log, okay? And this is one we use quite a bit, the natural log. And to indicate that it's something special by having that special base of e being kind of a special number, we change the way we write it. Instead of writing it log base e, we write it this ln, okay? So we'd say f of x equals ln of x, and that's how we denote the natural log of x. So you could either read it as natural log of x, or a lot of times we read it as ln of x, but we have to remember that ln is really for natural log, okay? And it has the exact same properties as the other log functions. It is still a logarithm. It just happens to have a particularly special base using that natural number e. So the natural log of 1 is still 0. The natural log of e, remember the base of the natural log is e. So it's really having the base of the log matching what we're taking the log of, and that's going to give us the 1. Natural log of e to the x is still x, and e to the ln of x is still x. So those same properties that we have for regular logarithms still hold true for natural logs. The natural log is still just a logarithm. It just has its own notation because of that special base e. Okay, so here's an example problem. Take a minute to read through that. And we're trying to determine the temperature increase within this car after 50 minutes. Okay? So the 50 minutes, that represents our x. Okay? We've got here, after Fahrenheit is the degrees Fahrenheit after x minutes. So we're really going to evaluate this function for f of 50. So we've got 13 4/10 times the natural log of x, which is now 50, minus 11 6/10. So all we have to do is evaluate that in the calculator. On your calculator, you will have a natural log, an ln button. And when we type that into the calculator, we see that's going to come out to be about 41 degrees Fahrenheit. So that should kind of make sense, because up here it says that the temperature in an enclosed vehicle climbs 43 degrees in the first hour. Well, 50 minutes is just a little bit short of an hour, and you can see that our temperature of 41 degrees is just a little bit below what the measured degrees are of 43. Okay, so there's just a simple application, something that we think happens every day in the summertime when we get in the car, we know it's hotter. It can be modeled mathematically by a natural log function. Okay. And here's another example of a logarithmic function and its application, talking about the Richter scale, or the magnitude of an earthquake. Okay. So the magnitude is represented by the value of r, this Richter scale value, and I is the intensity. And we have this formula here where r is equal to the logarithm of I, the intensity, divided by I naught. Okay, this I naught is what we call a zero level earthquake. Okay, So if an earthquake is 10,000 times as intense as a zero level earthquake, what is the magnitude on the Richter scale? So we'd have R equals the log, and remember when there's no base indicated, the log is base 10, okay? And the intensity is 10,000 times the zero level. So that's 10,000 I naught divided by I naught. Well, what happens when I divide something and they've got the same factor? Well, those two things are going to divide out, okay? So what I'm really left with is the log base 10 of 10,000. And we can evaluate that in the calculator. You have a log button on the calculator as well. So we put in log 10,000, and we find out that R is 4, okay? So that would be a magnitude of 4 on the Richter scale for an earthquake that is 10,000 times as intense as a zero level, okay? So we'll work on some more problems tomorrow involving logarithms, base 10, base b, and the natural log with the base e. So we'll see you then.